Okay, so in case you were thinking that John Giudice is speaking now, please note that it's not true. It's me who's speaking now, and John will be later. So this is your chance to leave. Okay, so we're at lecture number 3. And the sort of question I assigned for it at the beginning was, so what exactly are we doing, right? So far we just did gauge theory in high dimensions. And now I'd like to sort of make this more precise and say, actually, all this will come from some very well-defined string theoretic setting where all these gauge theoretic structures that we discussed so far will have a concrete realization, and as a benefit also an embedding into string theory, UV completion, and so on. But before that, so this, the subtitle for this lecture is From Higgs Bundles to Geometry. There's lots of literature on the side of the spectral covers and how this connects back to the geometry. So, of course, lots of literature on F-theory. And the more specific literature for F-theory and geometries of the so-called elliptic Calabi-Yau fourfolds is, I think the recent developments that are relevant for the kinds of questions we're asking here about gut models are, by these authors here. And then there's some nice way you can connect F-theory to M-theory and define sort of the effective theory for it, or at least attempt to do that. And it needs to be seen how powerful that really is via sort of this duality that I'll also discuss in a second. So there's sort of a partial list of relevant authors. I'm happy to add anybody who would like to be on here, so let me know. Okay, so finally we need to talk about F-theory. So I've been hiding this, as I said, for the reasons that I think the setup we discussed so far is very general. Right now, we'll have to actually start talking about, F-theory. So in sort of a one-line explanation, F-theory is really just a misnomer or a name for a non-perturbative type 2b vacua. We know in type 2b we have a complex coupling, tau, which is the axial dilaton, so the axion C0 plus I times e to the minus phi. And the nice thing about type 2b is it has a self-SL to Z duality, which maps tau to minus 1 over tau, more general A tau plus B over C tau plus D. So the idea of sort of VAFA was to not just treat this in terms of an additional coupling, but actually incorporate it into your geometry in a fashion that is compatible with this SL to Z action. And so the natural sort of setting for that is then, if you have SL to Z, to interpret this as actually the complex structure modulus of T2 or an elliptic curve more generally. Right? So T tau, this axial dilaton coupling, will then have a geometric meaning in terms of the complex structure of an elliptic curve. And if we like to sort of now compactify type 2b on a space down to 4 dimensions, including such an elliptic curve, we'll be looking at, elliptic fibrations of the kind depicted here. So this is the elliptic curve. There's a base manifold, and this is the total compactification. And for n equals 1 supersymmetry, we will be requiring that this actually is a Calabi-Yau space. So how do we actually, reach F-theory from other perspectives? One perspective is, well, as I just said, it's some sort of type 2b theory. Another sort of duality is one that I discussed at the end of the last lecture very briefly. F-theory is actually dual to heterotic in the instance when we are looking at special elliptic K3 fibers, Calabi-Yau fourfolds. Then it's dual to the heterotic on the elliptic Calabi-Yau threefold. So you can understand a lot of the duality from here to here by understanding this, these geometries and mapping these to these elliptic Calabi-Yau threes. Another useful sort of way to look at this, in particular if you would like to understand, say, the effective theory that's governing F-theory, is to start with M-theory. So you start with M-theory on a T2 or an elliptic curve. So let's first say that's a circle of radius RA and a circle of radius RB. And we can go to RA goes to 0 to, in the standard way, to just perturbative type 2A on a circle S1. And now doing T-duality, we can map that to type 2B. As we send RB to 0, do the T-duality, that's really type 2B string theory. If we do this in a fashion where these radii go to 0, but we keep this here fixed, the string coupling constant, then that is really not just some weakly coupled type 2B, but that's actually sort of what we would call an F-theory limit. So more generally, if this T2 is not just S1 times S1, but some general elliptic curve, E tau with, some complex structure modulus tau, then the limit from F theory to M theory is that M tau is GS, right? That's from here. That's fixed, but the volume of this elliptic curve goes to 0. Okay, so this is just essentially the bulk physics for the description of F theory in terms of different approaches. What we are interested in is where are the gauge degrees of freedom, and one of the promises that we sort of had in this type 2 type framework is they're localized on branes, and these are in this context 7 branes. Like in type 2B, there are 7 branes. In type 2B, we call them D7 branes. Here, we'll call them 7 branes. I'll be clear in a second why. So 7 branes in 2B, they source F9. So if you look at sort of your space-time and look at the direction perpendicular to that brane, that's a complex direction. And then if the 7 brane is located at some direction, in that direction Z at some point Z0, then you'll have to satisfy this equation here, right? So that's just a source term for the F9. Written differently, that's the integral of the dual dC0 along the circle at infinity has to be equal to 1. So if we solve this equation here, just locally, it means C0 was appearing here in the tau. That means the complex structure tau of this torus has to have some initial value tau of Z0 plus the logarithmic term log Z minus Z0. So in particular, if we go from tau to tau plus 1, this will pick up actually a monodromy. Right? So we're going around, there's this cut in the Z plane, and we pick up plus 1 as we go around there. So more generally, this monodromy will not be just the shift of tau, but can be a general SL2Z monodromy acting on tau, right? So that's why you can now label 7 branes, which have a specific monodromy by sort of representation of this SL2Z, and label them as PQ 7 branes in this way. So tau diverges at the locus Z0 of the 7 brane. In particular, so then, the complex structure of the elliptic curve is divergent there. In terms of the geometry, that means that at the 7 branes, these fibers become singular, right? So we had a compactification of elliptic curve over some base. When that becomes singular, that's precisely where we should be detecting the 7 branes. Okay? So now, before we get to, actually studying this more formally and actually getting down to the concrete details, I want to give you some intuition of how you should be thinking about this in relation to what we discussed so far. So we'll have a little picture show here. So this is the elliptic curve over the base manifold, right? So this is just the elliptic fibration. This is R3,1, and we said we're looking at 7 branes wrapping some cycle, in our case a 4 cycle, inside the base times R3,1. And what we just sort of briefly recapped is that the fiber, the elliptic fiber, over this sort of space where the 7 branes wrapping is singular. So, one of the cycles of this torus pinches. How we got matter was from these intersecting branes. What this means is that the singularity type of these fibers will actually increase. So 2 of these singular fibers will, over a further higher codimension locus, become even further singular, and then the Yukawa couplings will be when they become even further singular, right? So this is the picture, but then, we are not here to look at the pictures. We're actually here to do some math with this. So how do we describe elliptic curves? Yeah, so we need to understand elliptic curves, fibrations of elliptic curves, and the singular fibers that can arise there. So there's some classic theory, you know, going back many, I guess, 100 years or something, over elliptic curves over some field. For all purposes, that's the complex numbers. And we can always put these into the so-called Weierstrass form, which is, you know, y and x are complex coordinates. F and g, for now, are complex numbers. Y squared is x cubed plus fx plus g. So why is that an elliptic curve? Well, if we think of this in terms of y, this is a quadratic equation. So if I have two planes, this is the y plane, this is sort of the covering of the y plane, then the right-hand side is a cubic. It'll have 3 roots plus at infinity a point. And these 3 roots we can connect to 2 cuts from 0 to infinity and say 1 to lambda when these are these roots. And so now we can glue these 2 planes together, right? So this equation is saying we have a branched covering of the plane y, and now we glue these cuts together, and that's precisely going to give us this picture here, right? And that's just what you would call a torus. So definitely a genus 1 curve. Okay. So how do we detect when these you know, elliptic curves are actually singular? So that happens when 2 of these, you know, branch points collide. So for example, when lambda 1 approaches 1, these become one of these cycles when they shrink. So in terms of this cubic equation, right, we can just write it as sort of factored in this factored form. These are the zeros, right? That happens whenever A is B or A is C or is B is C. Now, if we rewrite that in terms of F and G that appear in the Weierstrass form, we can just expand this out. A plus B plus C is 0, and G is A times B times B, and so on. And then the condition that one of these terms vanishes. I don't know what happened here with the brackets. Anyway, really bizarre thing. Anyway, when the product of all these vanishes is precisely when one of these one of these cycles becomes 0. That is the same as now in terms of F and G, the condition that F cubed plus G squared is equal to 0. Right? So that's precisely what one calls the discriminant of this equation, y squared is x cubed plus fx plus g. So we're looking at now the loci when delta vanishes. That's when the gauge theory will be, you know, sort of localized and we'll be seeing the 7 branes. Okay, so the one question is then, what type of singularities can we have in elliptic curves? And so just if I look at elliptic curves fibered over one-dimensional complex curves, because I classified all the possible fibers, and you know, the way you understand these things is not by just looking at the singular equation, but you need to actually resolve the equation, find what is the intersection relation or the intersection graph of in the resolved geometry. So what you have is the elliptic curve. It has a singularity. You blow that up. In the blow-up process, you insert a P1, you know, in this resolution process, and you keep doing this until it's smooth. And then you ask, what is the intersection graph of these P1s? And what Kadara showed is that these graphs are always of this kind, where these lines are the curves. So if you now look at sort of the dual graphs, you'll see these are like the affine AN diagram, or the DN diagrams, or the exceptional diagrams. So there's like sort of almost like an ADE type classification underlying there. What we're interested in is a little bit more, you know, complicated in the sense that we're not just interested in elliptic curves fibered over one-dimensional complex manifolds, but we like to have 4 folds for F theory. So we need to have a complex 3-manifold. So this Weierstrass equation is now not just a complex equation, but it's actually an equation where these functions f and g vary over your base manifold. Right? So they're now actual sections or bundles of this base manifold B. So if we now pick some local coordinate z in the base, and we ask, so can I engineer a specific type of singularity there? In fact, how do I detect that there's a singularity? So z equals to 0, right, in B3, that's a 3-manifold, z equals to 0 will give us divisor in B3. Let's call it S. That'll be where S gut is going to live. So this divisor S, I'd like to know how do I detect that there's a singularity over this locus z equals to 0. Well, I can look at F, expand it in terms of this local coordinate z, and do the same for G. And then ask, is the discriminant computed in this way, vanishing as a function of z. And when it does, then indeed there is a singularity above this divisor, which is a 4-cycle inside the base manifold. Okay, so delta is equal to 0 is an equation in B3, and it can have many components. We're interested in a component that corresponds to, say, one specific divisor that we'd like to study. So delta will have some expansion in terms of the z, and the kind of, vanishing order of that will tell us what type of singularity we have. Okay, so this is the Kodaira classification of all the singular fibers. It's sort of the way the labeling goes. The IM type singularities are the ones that are either SUM or SPM groups, and the IM stars are the SO odd or even groups. And then there are sort of these outlier cases, which are the exceptional groups, and then the low rank ones. So I0 is what you should read in terms of it's not singular, right? So the vanishing order of F and G and delta, so delta is vanishing order 0, so it's not singular. And I1 singularity is order 1, so that really corresponds to a single 7 brane. And then I2 singularity is order 2, that's an SU2 gauge theory, etc. Right? So this is the way you read this is the vanishing order of F and G and of delta, and then from there you can read off the type of singularity, that's just sort of a label, but this is really where you read off the kinds of gauge groups that you will get there. Okay. So one sort of interesting thing is to ask, if I would like to engineer a specific singularity, given the Weierstrass form, this is not the most sort of direct approach to write down a singularity. There's actually a very nice way to do this called the Tate algorithm, where you don't start with this f squared is x cubed plus fx plus g, but this more general Weierstrass form. And then there's a very specific prescription how the vanishing order of these coefficients here determines the type of singularity precisely. Right, so here there was just a statement, if f vanishes to this order and delta vanishes to that order, then you'll get this kind of singularity. Here I'll say, this is an equation. If I would like to have a singularity of type so-and-so, I have a vanishing order of these coefficients given as in the Tate algorithm, and then at z equals to 0, that singularity is realized. Okay, so this algorithm is sort of a neat thing that appears, I think, it has a more number theoretic origin, but it's, it's useful in this context as well. And one question in particular is when you apply this to, elliptic fibrations over high-dimensional bases, one question is that you can actually bring it, a singularity of this kind always into this so-called Tate form, right? So there's a question, given the Weierstrass form, can you actually globally map it into this so-called Tate form, which is a canonical form for the singularity? And for that, this Tate algorithm is sort of the tool to test this. Yes?
Could you say
where's the question?
Yeah, isn't the Weierstrass form always a special case of the Tate form, the way it looks here? If you just
sure, you can. There's a nice shift. You can go from one to the other.
No, but if I just said A1 equal to A2.
Sure, but what I'm going to tell you is that if I give the vanishing orders of these guys, then
what would be the case where you can put it into a Tate form?
I will explain to you in 1 second. Okay, so. We will get to this in the moment. Because there's really, when you can put in a Tate form, you'll have to make a coordinate change that's not holomorphic, right? So for example, in order to put this into the Tate form, you need to shift some of the coordinates. And there'll be a problem in some of the cases when you cannot shift because by a holomorphic sort of shift.
Okay, so this is maybe very naive, but isn't the Weierstrass form just a special case of the Tate form, the way it looks here?
Sure, but the question is a different one, right? So I give you some singularity. Yeah. I ask you, what is the singularity? This algorithm will tell you it's a singularity of this and this kind. Yes. On the other hand, if you want to engineer a singularity of a specific type, there's sort of a question, can you start with this Tate form? Is that a globally well-defined, is that the most general sort of starting point? And then the answer is, in most cases, yes, but in some cases, no. And I'll give you an example when it's not. Okay? But thanks for the question. Are there any other questions? Okay, so this algorithm is really sort of about this canonical form for the singularity. It's very sort of straightforward. So I'm just going to go through the first couple of steps, and then there will be a whole inductive proof that's when it works and when it doesn't work. So the starting point is we have some Weierstrass form with the sections F and G having some expansion in the coordinate z. So z is where you're asking, is there a singular fiber above the locus z equals to 0 in the base? Now, the discriminant, right, we said is where we detect where the singularity is located. We can just expand it in terms of z. So if z does not divide delta, then it's smooth, and that's what we would call an I0 fiber. Nothing is happening, no 7 branes. If z divides delta, then there exists some u0 so that I can solve this equation here, right? So I can solve that by setting f0 is u squared and g0 is u cubed. Plugging this in solves this. And then there's a shift of coordinates that brings it always into this form here. Now, if you sort of haven't seen the Tate form before, this is precisely what a Tate form for an I1 singularity is. And this corresponds to, there's this, 1 power of z dividing the discriminant. That's an I1 singularity. So it has a vanishing order of the coefficient of x. That's of order 1, and all the other ones are of order 0. And that's really, from the gauge theoretic point of view, is you have a U1 gauge symmetry there, the single 7-brane. Now, if z squared actually divides the discriminant, right? So we have this expansion here. So actually z squared divides a discriminant. And we need to look at the remainder here, where, this object here now has to be of order 0, right? So this is, it can only contribute, if at all, to the next order terms. So we can actually just set this to 0 to leading order, this piece here, so this to 0. And then just we get the Tate form in this form here, which is the Tate form for an I2 singularity, where this term has now vanishing order z squared. And so now we continue, and so this looks like, okay, so you just keep going through this whole thing. At z cubed, something interesting happens already. So at z cubed, the remaining discriminant looks like this. This is the quadratic piece. And now we can have to ask, so if z cubed divides delta, first of all, there's some S0 mu, such that this u and F1 take this form. And then there's a question whether this mu here actually has a square, has actually zeros or not. If it has no zeros, then we can just set it to 1. And then this whole thing here actually will have a square. And then we can just put this by a shift into the Tate form for SU3, which is the I3 singularity. The condition that this mu doesn't have a 0, so we actually can just put it to 0, and u actually becomes a square. That condition here is sort of indicated by this S, which says split. So this is sort of one case where you can get from the I2 singularity, enhance it up to an I3 singularity. However, if mu has a 0, then there's actually no shift to bring it into any kind of Tate form. In fact, you would initially expect that this has a Tate form for this SP1 singularity like we had. If you remember, these two up here on the same level, right, in this Kodara classification at rank 2. But, there's actually no shift of the coordinates so that you can bring it into a global Tate form that looks like this equation here. This equation here with the vanishing orders that are sort of prescribed in the Tate form. So here, there's actually only locally, a shift of coordinates where you can bring it into the Tate form. More generally, you actually only have some more relaxed, generalized Tate form for these kind of models. So at this point here already, the distinction between going from an SU2 to either an SU3 or an SP1, at this point you already get an obstruction for mapping it into a complete Tate form without having to divide by the zeros of one of these sections, right? So if you actually do the shift, you have to divide by S0, and S0 can have zeros. That's sort of the problem.
What's required
No. So indeed, the initial Tate algorithm, right, applied to these kinds of F-theory things by Breschatki et al. Was to just look at local changes of coordinates. You completely ignore global issues. So you just, so then you can always bring it local into Tate form. There's no problem, right? So this just continues through this algorithm. The point is, however, right, if you would like to have a global Calabi-Yau fourfold with a specific type of singularity, there's a question, can you always bring it into this form? Is that the most general starting point or not? And then you need to address, is that actually a global change of coordinates, or isn't it? And the statement is already here, right, which is just going from rank 1 to rank 2 groups, that appears already. Yeah. So now, in fact, you can go inductively, so you can do it up to SU5. You see what the pattern is. Just inductively show that you can then put it always into Tate form, except for a couple of low-lying cases where you have a generalized Tate form. And then there are some really outlier cases where you just don't have a Tate form at all. So that's sort of something you need to keep in mind whenever you're applying such, when you're writing down the Tate form for some singularity, you need to at least be aware that this may be a restriction in what you're doing. Okay, so one example for an outlier case is this E6 that's deformed to an SUA5 singularity that actually doesn't have any Tate form at all. So apart from these groups that appear here, there's always a global change of coordinate that you can make to get into this form that I wrote down here. And now you wonder, so if I have some specific singularity, what is the vanishing order of these sections A? And these are given here. So again, this is the type of singularity. This is the gauge group that you will generate in this way. And then this is the Tate table telling you if the vanishing order of these coefficients is as given in this table, then the discriminant will vanish up until this order here. And there's a singularity at z equals to 0 that realizes the gauge group as in the second column. Right? So that's a pretty general thing. And now if you'd like to start with SU5, we need to focus on this row here. So SU2 n plus 1 for n is equal to 2. So the vanishing orders of these coefficients is 0, 1, 2, 3, 5, and 5. And so then we just read off this is the Tate form for SU5. Right? So you have an SU5 singularity, bang here, right, at z equals to 0. I will get to this because, so I call these guys B, and it's actually the connection between the Higgs bundles and the Tate form is almost immediate. So you can take a local limit, meaning you can go close to, you can look at the geometry that's close to z equals to 0, and then you will get from this right away the spectral cover. Right? So this Tate form is like really encoding for you geometrically in a global fashion this data that we talked about before. Right? Whereas a general, y squared is x2 plus fx plus g, you're like, okay, so yeah, maybe there is an SU5 singularity, but it'll be much more obscure what the connection to these gauge theoretic data is. Okay. So more precisely, we have to discuss a little bit about the geometry here. This equation here is really written either in terms of a P2 bundle, where each of these sections, so there's one trivial piece that comes from the section of P2, the hyperplane class, then X and Y are sections of KB to minus 2 and KB to minus 3, respectively, but KB is the canonical bundle of the base. Or we can embed this directly in some weighted projective space, P1, 2, 3. And so these kind of spaces are Calabi-Yau spaces because these are really sections of the anti-canonical bundle. And by adjunction, the normal bundle is really also the anti-canonical bundle. So the total canonical bundle of this hypersurface here is actually trivial. Okay, but what we'd actually like to see now, and that's going back to your question about, why is this a good form, is do we see now in particular all the structure that we had in this discussion of the Higgs bundles. So this is an SU5 singularity. Indeed, when you compute delta, it'll have vanishing order z to the 5 plus higher order terms. Now, the base that we're looking at, right, so these BIs, they're all sections over line bundles over a three-dimensional base. In the sort of standard Kodaira way, where you just had a one-dimensional base, all you discuss is the singularity in codimension 1, meaning along z is equal to 0. But here, we'll have a lot more freedom because, these are really, three manifolds. So we can look at higher codimensional loci. For example, we can ask, when delta 5 is equal to 0, right, we're looking at a locus in B3 that z equals delta 5 is equal to 0. So that is a codimension 2 subspace inside B3. In particular, if you look at the discriminant for the SU5 singularity in terms of these B's, right? So just plugging that in, you can compute that, and so you see that delta 5 is actually the product of B1 to the 4 times this combination, and you will recognize this combination is precisely something that we've seen before as this P is equal to 0 for the matter, for the 5-bar matter. Anyway, so there are two codimension 2 loci where the singularity type stops being just z to the 5, but actually becomes z to the 6. Yes? So the singularity type enhances from z to the 5 to z to the 6. In fact, there's also codimension 3 loci where the singularity type actually enhances up to z to the 8. And we can look at these loci because we have high-dimensional bases, and so looking at z equals b1 is b2 is 0, or z equals b1 is b3 is 0, that's a point on b3. And the statement is then, if you move to that point on B3, the singularity type will actually enhance even further. So one question is, what really is happening there? How can we describe the fibers along these loci? And so the Kodaira classification is really something that's technically only applicable in codimension 1, meaning along z equals to 0. And that problem we solved with the Tate algorithm. This is already an SU5 singularity. So the question is, what happens along these codimension 2 and 3 loci? So there are some intuitive things that we should keep in mind before we actually go and really construct the fibers, resolve the fibers, and look at what's happening there. So the heuristics one is, z equals delta 5 is equal to 0. Is like we have a GOT7 brane that's at z equals to 0. And then delta 5 is equal to 0 is a second condition. We can think of that really as a flavor brane coming and intersecting that over a codimension 2 locus, meaning a curve inside S. And so from the intuition that we'll learn from the last lecture, that's really should be generating as matter. And likewise, if you look at the codimension 3 loci, z equals delta 5 is delta 6 is 0. That should be corresponding to 2 flavor branes coming in, intersecting, and giving rise to the Yukawas. And that's sort of, mirrored in the fact that the discriminant will have higher and higher vanishing order as you go to these higher codimension loci. Yeah, so the picture would be then the discriminant is either vanishing order z to the 6, or in fact z to the 8 for the codimension 2 and codimension 3 spots. So G, there'll be some higher rank G that will be located there that's then sort of Higgs down to an SU5, generating all this matter. So that picture of how we understood Higgs bundles, how they, starting with an E8, Higgs it down to an SU5, this picture should emerge here from these higher codimension loci in the geometry. However, that's sort of just words attached to looking at the discriminant, doing a Taylor expansion. So what we really have to do is to understand what's happening in these fibers, resolve them, and actually show what is, the structure there. So that's what we'll do. So we start with the Tate model. It has a discriminant that has vanishing order z to the 5. And so first of all, it is singular. It's x equals y equals to z is equal to 0. How do I see that? Well, singular means the tangent space there degenerates, so I need to take the derivatives in all these directions and set x equals y equals to z equals to 0. And indeed, if we take the derivatives, you can check, in 1 second, setting x equal y equals to z equals to 0 indeed makes all these derivatives vanish. So it's singular there. How do we resolve this? So this is now, the locus in, the z equals to 0, so this is really the S-gut surface. We can remove this point here. So it's very similar to how you resolve the conifold singularity. Because this is sort of a slightly more complicated context with a higher dimensional singularity, what we do is we remove this point here by making x, y, z projective coordinates. Right? So let's call these x, y, zeta 0 are projective coordinates on a P2. The P2, I will say, is given by an equation zeta 1 is equal to 0. Zeta 1 is a new coordinate that I introduced that characterizes this new P2. These are just, projective coordinates on there. Now, when I have zeta 1 is equal to 0, that's just the locus that initially was x is y is z is 0. Yeah? So indeed, that locus now, where x and y equals z equals to 0, that used to be singular, is now replaced by zeta 1 is 0. So at that locus, precisely a new P2 opens up. Right, so that's very much like this resolution that we did yesterday with the dPn, except that there wasn't a singularity. We were just blowing up a point on P2. Here, there's a singularity in this fourfold, and we're resolving it in this way by inserting a new P2, removing the singular locus. Right, and this new, divisor, which we'll call exceptional divisor, this zeta 1 is equal to 0, is precisely this additional P2 that's inserted at a singular space. So this geometry, once we've done this and plugged this back into the geometry, we can check it's still singular actually. So at x equals y equals zeta 1 is 0. Again, take the derivatives, put them to 0. We see it's still singular, so we can introduce a new P2. Again, do the same thing. X, y, zeta 1 are now projective coordinates on a new P2 that's defined by the vanishing of a new section zeta 2. And indeed, then after doing this second resolution, the geometry takes this form. So that looks very horrible, right? So there's all this stuff going on. But if you sort of boil it down to the basics, it really just looks like y times y tilde is zeta 1, zeta 2 times z. So that's very much like a conifold type singularity, slightly more complicated. So for actually an SU2k plus 1, the structure will be only mildly different. You'll have to do k such resolutions, and you'll get k exceptional sections. So what is the actual, what's going on in this thing? So this is already giving away the punchline, but here, how do we understand this? So if I said zeta 1 is equal to 0, we said that's a new exceptional divisor, and zeta 2 as well. In fact, zeta 1 and zeta 2 are both, not irreducible. Zeta 1 is equal to 0 is the product y tilde. So really, there are 4 exceptional divisors here. So zeta 1 is 0 with y or y tilde, and the same for zeta 2 with y or y tilde vanishing. And all these 4 are new additional divisors in your geometry. And now you can ask, what is the intersection between these divisors here? And what you find after doing the calculation, so what you need to do for that is do the actual intersections, work out what are the intersection relations here. What comes up out of this calculation is that these 4 divisors that we get from the resolution, they have an intersection that's given in terms of an A4 Dinkin diagram. And then if you intersect them also with zeta 0, which was sort of the initial coordinate z became zeta 0, then they close to an affine A4 Dinkin diagram. Right? And so that is not a surprise, right? We said that Tate models will have the structure of along the singular locus, the fiber will be sort of an A4 type singularity. Now you will wonder, in Kodaira, we said the fibers were P1s intersecting in this diagram, and Kodaira classified them in this way. So really, when I'm drawing this here, I'm thinking of these exceptional divisors are really the P1s fibered over S-gut. right? So that gives us the divisors, each one of these, so P1s here, fibered over S, gives us one of these d alphas, and, computing their intersections essentially corresponds to intersecting this divisor here with another P1 here, and that gives precisely the Cartan intersection matrix of A4, or the affine A4 actually. Okay, so the way that these P1s that appeared in Kodaira up here are really in the fibers here, and these Cartan divisors, these exceptional divisors, are the fibrations of the P1s over the surface S. Okay, so if doing this calculation is sort of one thing. So here we really construct it now. We resolved the geometry. It's now smooth, at least from the point of view of looking at codimension 1. Now let's look at higher codimension. So we said, the base is three-dimensional, so we can look at coordinate z equals to 0, but also another coordinate vanishing on the base. So for example, if I look at z equals to 0, but also b1 is equal to 0, and check from this, equation that we obtained after the two first resolutions, at y equals zeta 1 and zeta 2 is b1 is 0, that actually is still singular, right? So you can look at the derivative. On this side, it's clear, taking any of the derivatives, we're setting zeta 1, zeta 2 to 0, that goes away. And then y derivative will leave us with this here. This goes away, so you're left with b1x, right? So b1 is 0, and d is equal to 0 is still a singular locus. So to, remove that singular locus, what you have to do is you have to remove, for example, the simultaneous vanishing of y and zeta 1. So this is now very similar to conifold, right? This is x times y is equal to z times w. So now we remove this locus where these two vanish by replacing y with a projective coordinate y, zeta 1 with a projective coordinate zeta 1. So y zeta 1 parameterize a new P1, the new coordinates associated to the vanishing of these, right? So delta 1 is equal to 0 parameterizes this new P1. Whenever initially zeta 1 and y vanished, that's now replaced by delta 1 is equal to 0, and the whole P1 opens up. Once we do this twice, both to y and zeta 1 and y and zeta 2, the smooth geometry is now given in terms of this. So this geometry, we can check explicitly, is now smooth in any codimension. You take the derivatives, and you will always get that it's completely smooth. Now, what we were interested in is what is actually the structure of the fibers. For example, along this B1 is equal to 0 locus. So naively, right, we're saying there's this A4 singularity, meaning this affine A4 intersecting P1's fibered over S. And now we're looking at a sublocus where B1 is 0. And B1 was the discriminant component of the next order discriminant, so delta 5 is equal to 0, contained B1 is 0. So what we expect here is that the A4 actually becomes either an A5 or a D5 singularity. So in the fiber, there should be additional components appearing that enhance the fiber in this way. Okay, so naively, this is sort of what you would think, and in fact, this is also what happens. So the SO10 or SU6 fibers appear there, and when you go to the codimension 3, which would mean we, in addition, have another curve coming in here, and we're looking at a point on B3, then naively we expect an SO12 or an E6 fiber. So what's interesting is there is indeed an SO12 fiber, but there's no E6 fiber, and that sort of caused a lot of sort of trouble. When Issel and Yao came up with this sort of observation that the E6 fiber was the cool thing about these kind of constructions, that you had E6 giving the top Yukawa coupling. So one sort of question is, how do you actually generate the top Yukawa coupling despite the fact that you don't have this E6 fiber sitting over that point? So again, to answer all these questions, about the higher codimension fibers, we need to look at what actually happens to these exceptional divisors that made up the A4 fiber. as you go, for example, to B1 is equal to 0, or P is equal to 0, which are these two codimension 2 enhancement loci. So at B1 is equal to 0, you can look at the exceptional divisors that we had, A1, A2, to D minus alpha 1 up until D minus alpha 4. And two of them will remain irreducible, but in fact, these two here, which you'll see from zeta 1 and zeta 2 is equal to 0, they'll become reducible, right? So their equation will just become something that factors only along the locus B1 is equal to 0. Right? And so you see that if you set, for example, zeta 1 to 0 in B1 to 0, then this actually becomes a factored term here. So then you get, for example, splitting D minus alpha 1 into, now intersected with B1, so that was a divisor, that's intersecting with another divisor, that will be a surface now. And there'll be two surface components for this one, and the alpha 4 root, or the divisor associated to the alpha 4 root splits into 3 components. And now, what are these labels here underneath these surfaces? Well, you can ask, so what is the intersection relation of these guys with the initial Cartan generators, right? So with the initial Cartan divisors. So these guys here are precisely in intersection with alpha 0, alpha 1, 2, 3, and 4. And if you look at what kind of, weights, it isn't really weights of some, representation of SU5. These are precisely weights that appear in the 10 representation. And then similarly, if you look at P equals to 0, only one of them splits. And the splitting, again, computed from the intersection with the original Cartans, gives you a splitting into representations of the SU6, of the 5 bar, coming from the enhancement to SU6. Okay, so despite the fact, that we haven't really sort of looked at the intersections of the fibers along the codimension loci, you already see as you move from, say, this A4 singularity to this codimension 2 locus, one of these roots here splits, and one of these roots splits, and likewise here, and they split into representations precisely, corresponding to the groups that you would expect that these loci to appear. Okay, so that this codimension 2 locus is sort of, then, you can also then go and actually look at the intersection diagram here, and you will find that it is given either by a DN or an AN Dynkin diagram of one rank higher. But this is sort of, I think, a nice way to understand, indeed, these generators split, and there'll be additional degrees of freedom corresponding to transforming in weights of the 10 or the 5 bar representation of A25. Okay. And so with this kind of logic, you can now continue and look at this E6 point. And we said if you look at the fiber over this E6 point, this B1, B2 is Z is equal to 0, these matter surfaces, right, they'll also split. If you compute the intersection of these things, then actually you don't find an E6 fiber. However, the splitting is actually in the following way. So you start with a surface, right, which is, say, in this with this weight here that appeared earlier in here, I think, this one here. So that's in the 10 representation. You intersect it with B2 is equal to 0, right? You get curves, and actually it becomes a reducible component. It splits into 2 curves. Calculate the intersection with the Cartans, determine the weights of this, and you actually find it splits into another 10 and another 5 representations. So this is precisely, the kind of splitting that you expect from 10-10-5 coupling that would generate an E6, would be generated at an E6 point and gives rise to the Topiokawa coupling, right? So far this is just how the geometry will work, right? The physics of this is there will be, M2 branes wrapping each one of these, P1s in the fiber. As they move to this point, B1 is B2 is Z is equal to 0. One of them will become reducible and split into another 10 and a 5 representation. And so at that point, at that exact point here, all these guys will be equivalent. And so really there's like a 3 chain connecting these P1s that becomes, 0 size at that point. And so you can really then integrate over that and generate a non-trivial Yukawa coupling. So in this way, despite the fact that there's no fiber that really is realizing this E6, you can get consistency with what in the discussion of top Yukawa couplings in the gauge theory one would have expected. Okay, so this is sort of the depiction of what I just explained. So here along these matter curves, right, we said the A4 fiber will split into either 10 representations or 5 representations. And then as you move to the point, the B1 is B2 is equal to 0, E6 point, actually one of these curves will become reducible and split into two curves that correspond to the matter that meets all in that one Yukawa coupling point. Okay, so you can also do this more generally and write down the resolutions and look at, in fact, here when I did the small resolution at the very end, I picked two coordinates here, so y zeta 1 and y zeta 2 to arrive at this equation here. There's sort of a network of small resolutions related by Flob transitions that you can study here. The physics will not change, but it's sort of, these will be distinct kind of ways that the matter curves will actually split. So there are slightly different phases of the theory that you'll get by looking at different small resolutions of this singularity. And that only will affect, of course, codimension 2 and codimension 3, because we're starting already with this geometry that's resolved in codimension 1. Okay, so let's see, so where were we? Yeah, so I just made for the last 5 minutes. So you can look at all these, this whole Tate table and really ask, so when are these fibers actually Kodaira, when are they not Kodaira, and draw all kinds of funky pictures. So I'll just maybe click through them. So this is like the AN, then you can see how it extends. This is sort of the splitting along these various loci. And then there's some very funky fibers which you get. In particular, these are the intersections of the fibers when you do the following thing. So far we've stayed well safely below anything that fits into, an E8. If you look at fibers, for gauge groups that, are just of some higher rank, you can ask, so if you started with, say, an SU5, we went up to SO10 and then also to E6. Now, if I sort of ask what is the fiber structure of an SUN, and I go to these loci, which followed from AN to DN and then to the exceptional locus, there's really no way you can go to this higher exceptional locus. Right? So what actually happens is you get, indeed, completely non-Kodaira type fibers at these intersections, at these loci that would correspond to the higher rank generalization of these E-type loci. But actually what is even more interesting at these things, these are so-called non-minimal singularities, you'll actually get not just P1s in your fiber, but actually higher dimensional components, meaning surface components in the fiber. And so, coming from sort of this M-theoretic point of view, you can ask, so wrapping on these P1s, you get, M2 branes wrapped, you get these gauge degrees of freedom. When you now look at fiber components that are higher dimensional, you can wrap M5 branes on these, right? So what is the low energy theory that you obtain by looking at these non-minimal sort of fibers? And so I think that's something that really goes then beyond these gauge theoretic constructions. Okay, so this is sort of now the one slide that really connects very precisely what we discussed in this lecture to what we discussed in the last lecture. We said, we always look at this kind of Tate form for, say, an SU5 singularity like here. And one question is that should be, describing 7 branes and a Calabi-Yau fourfold, wrapping some surface S times R1, 3. And for the last 2 hours, I discussed the effective theory on 8-dimensional gauge theory on this kind of space is characterized by a spectral cover, line bundle on spectral cover, and so on. So how do I actually see the spectral cover arise from that geometry? And it's really sort of a one-line thing. Look at the Tate form. So it can look at a divisor inside this geometry given by y squared is x cubed, or just by setting this piece here to 0, right? That's a, an equation inside this Calabi-Yau fourfold. And now I can take a local limit in the sense that I set some coordinate t is y of x, and take a limit when we go to z goes to 0, t goes to 0, but we're keeping this ratio fixed. Yeah, you just apply this limit. It's like zooming into the vicinity of the locus z equals to 0. And then I can sort of apply this to this equation, and in fact, just plugging this in, taking this limit here, taking that here fixed. From this divisor here, you just arrive at t to the 5 times the spectral cover for E8 Higgs down to an SU5, right? And where these BNs are now restricted to S and are precisely the coefficients that appeared in the spectral cover that we have here. Okay, and all these matter loci and Yukawa coupling loci, right, that we described in terms of when the eigenvalues of the Higgs bundle vanish are encoded in the vanishing of these sections, right, like we discussed here. So all these higher codimension loci. 1 second. All this here is then precisely mapped to what we discussed 1 hour ago. So B1 is equal to 0 corresponded to lambda I is 0. This is equal to 0 with lambda I plus lambda j is 0, and so on. Okay? So in that way, you connect this geometry, which is a global Calabi-Yau fourfold, with this SU5 singularity directly to this gauge theoretic data. Yeah? So engineering such geometries gives you automatically sort of the data that you need to construct the spectral cover. And then there's sort of another benefit from this resolution, which is something that in the subject has been sort of the main interest for the last year or so, is you can, from the resolution, you actually can construct all the G-fluxes. And so the G-fluxes really, once decomposed, will precisely correspond to the vector bundle data in the spectral covers and generates all the chirality. So the way we construct the G-fluxes is in terms of, again, dual surfaces. So I can, I'll discuss that maybe in the discussion session today if you want to know. So G4 are 2 forms on this Y4, satisfying supersymmetry condition and quantization. The C2 of the Calabi-Yau you need to calculate from, again, the resolution of the fourfold. And construction of this G is now possible by looking at the dual surfaces, taking linear combinations that satisfy precisely these 2 conditions. And that's sort of a really constructive way to get G-fluxes, then look at models that generate chirality. Another sort of refinement of this story is when you look at Tate models, where you have sort of additional sections. That was done recently by Christoph and collaborators. And there you need to sort of, what you're doing there is you're refining the spectral cover to have a factored form, meaning you'll get additional U1 symmetries. You're translating that into a condition on this Tate form here, right? And then you get globally a well-defined U1 symmetry from this refined Tate form. Okay, so that was all I wanted to say about the geometric part. And so tomorrow what I'll do is I'll put this all together and actually do some model building and see what we can actually achieve with these type of constructions. Okay? Are there any other questions? Yeah.
So my question is just a basic question. So you start straight away from algebraic varieties, right?
Yes.
In principle, you're supposed to consider any possible complex manifold, right?
You mean for S?
No, well, yes, for S or for the threefold or fourfold, whatever, right?
Well, no, so I would like to have n equals 1 supersymmetry in 4 dimensions, right? So that imposes that it's Calabi-Yau.
Yeah, but I mean not necessarily algebraic one. Any complex
That's true.
manifold. Also, so is that true, first of all? And the second question is also this Tate model, Tate ADA classification of singularities, or Kodaira classification of singularities, that also, as far as I understand, applies to, like it's an algebraic classification. Is there a topological classification, which would in principle, like you want to consider a toric vibration over some complex manifold, right? Is it clear
this is not toric.
Look like
so one point maybe that I should make is that this is not toric, right? So this is completely algebraic, and it's, I think, as general as you can do with these kinds of models. So there is an assumption in here that I can write the equation for this elliptic curve, in terms of this Weierstrass equation, fibered over the base manifold, right? And that has a section and all that. But that is the starting point, and I think from there, it's an algebraic process. If you would like to reformulate this in terms of toric data, you can do that, and people have done this. But, here, this is a very explicit way you can get the most general kind of, resolution that you can think. In fact, we were discussing this yesterday, so there seems to be some, when you look at the resolutions, right, that we looked at here, so there's, in fact, from this algebraic point of view, the types of resolutions that you can get can, in fact, be slightly more general than what you can get maybe torically. Because, so torically, what you would do is you would just think of this in terms of y times y tilde is equal to zeta 1, zeta 2 times something else, and then you resolve that geometry. So you don't really see all this refined sort of structure of the actual algebraic variety.